Hello there, Avon High School ACE College Algebra 2 students, or any other students who happen to be tuning into the video. Perhaps you were directed here because you were interested in studying the discontinuities of rational functions. And this is what this particular lesson is all about. It coincides with Unit 12, Section 3 of the curriculum that we use at Avon High School. Very suitable for any pre-calculus class that's studying rational functions and wants to get a little bit more in depth about why there are discontinuities and what types of discontinuities could occur. So the objective here is to discover properties of rational functions analytically and include point discontinuities and vertical asymptotes. So there are two different types of discontinuities in functions. And in my particular class, we've already talked about the different branches here, and that we can have these removable or we can have these non-removable discontinuities. But we haven't really subdivided either of those two types of discontinuities. And when it comes down to it, the removable discontinuity really only comes in one classification, and that's going to be referred to as a point discontinuity. Whereas the non-removable discontinuity is now going to have two subdivisions. We're going to talk about an infinite, and we're going to talk about what's generally informally referred to as a jump discontinuity. And we will see quite a few graphs of these particular discontinuities. But to get things started, I want to talk about what would we expect the description of the graph to be in either of these cases. When you have a point discontinuity, what is it that we technically or typically see from the graph? Well, I'm going to scroll down because we're going to see a sketch of one right there. There's a graph that has a removable point discontinuity at x equal 1. So one of the most telling characteristics is the fact that we would have a hole, that there would be a hole in the graph. But I don't want to just stop there, because it's possible that you could still see this open circle, this whole idea, in a different kind of discontinuity. So I want to come back to this in a second. For right now, I don't mind if we just want to stop there, because it's pretty clear that that's what we see here visually. But I want to kind of expand on that. So let's move over to the non-removable discontinuities, and we talk about the jump discontinuity. I'm going to do that first. It's the one that we've already talked about in class. And I think that's very characterized by what you see in the graph here below. The graph has this complete break, or we could call it a jump. So we see a break. I don't like to use the word jump in sort of the description, because we are describing what is a jump discontinuity, but I'm going to allow that here. So we're looking at something like this. Two separate parts of this graph that exist sort of independently of each other. Now the infinite discontinuity, that's the piece that's going to be new, at least if you're watching this and you're one of my students currently. Here we see the graph below that has this non-removable infinite discontinuity. And we see that's characterized by this dashed vertical line, and it's very likely that we all are very familiar with that from perhaps Algebra 2 class, and that's referred to as a vertical asymptote. The idea of the infinite plays a part in that these pieces of this graph that I've circled will just head towards positive infinity, or they will head towards negative infinity, and meanwhile get closer and closer to that vertical line x equal 1, but yet never touch it. And this is going to be a very important idea as you students move into AP Calculus in the future. Now, if I go back to my first description of the point discontinuity, the reason why I don't like just saying, well, there's a hole in the graph, is that one could make that argument for the jump discontinuity. There could be a hole in a graph right there, or truth be told, there could be a hole here as well. There's nothing that says that we have to have the function defined at 1. So I want to preface this, or add to this, that there's a hole in the graph without there being a break in the graph. And for right now, those will work as informal descriptions of these different kinds of discontinuities. We will formalize these in much more detail as we move into calculus. Now, each of these will have a domain and a range that we can discuss. So if we look at our first graph, that's the one with the point discontinuity, we find that every value of x seems to be defined except the one where the point occurs, and that's when x is 1. So we could certainly write it as such. Include all the real numbers except for 1 using interval notation. That's the way that we typically go about doing that in class. And if we think about the range, that would be all of the acceptable y values. And we find out that these arrows will indicate that we're going to include all of our y values. Will we include the y value where the hole occurs? Well, the answer to that would be a yes, because of the point right there that will be included. So we could say all real numbers, or negative infinity to infinity. Now, if we look at our infinite discontinuity, the second graph, we find that we have a very similar situation with the domain. All of the x's are included until we get to that vertical asymptote, which is occurring at 1, and then we can pair that up with 1 heading on to infinity. When we talk about the range, again, the arrows pretty much tell the tale, in that we're going to include all y values in this problem. Now, if we take a look at the third graph with the jump discontinuity, we once again find that the x's that are included would be all values again until we get to the 1. But as we get to the 1, we realize that because we have an included point there, we could say that the domain of this function is every number. We could talk about the range. Again, the arrows will tell us all that we need to know, and that all the values beginning with negative infinity up to, and not including or stopping at 5, but we could see how this arrow is going to extend and gather larger y values, and thus infinity would be the upper bound for the range there. So that takes care of our first page. As we move to the second page of the document, of the notes that hopefully my students are working with, what we see is a page that just consists of 4 graphs. So it says, use the graphs of these rational functions below to complete the table that you will see on the following page. Given are the equations of the functions, their graphs, and the coordinates of any point discontinuities. So for our first function called f of x, we see the rational function. Here its graph is depicted, and we have the coordinates given of the whole at the point 3 and 7/5. Now, it's very important that we understand that I'm not going to use a graphing calculator technology to depict these, because no matter how robust the calculator technology might be, they're not going to do a very good job of showing you these point discontinuities, unfortunately. So it's best that these are rendered a little bit more specially, and that's what I've done ahead of time. Now, if we go to the g of x graph, we see that the rational function is given, and we do have the sketch given, and a hole is occurring now at -3, +0.5. H and P are given below, and again, the same ideas are occurring. Each of these 2 graphs has a point discontinuity, one at -2, 1, the other at -2, -1. So I'm going to go ahead and move to the second page of this, the third page, and we see our first example that asks us to use the graphs on the previous page to complete the information asked about in this chart. So we begin with part A, which talks about the first function, f of x. And you'll have to forgive me that I will be going back and forth between this page and the previous page. But when we can just answer questions analytically without looking at the graph, we're going to strive to do so. So for part A, in the first column, it asks us to rewrite the function in completely factored form. So they're saying to us that this f of x can take on a little bit different look. We're going to look at this numerator, and we're going to look at this denominator, and we're going to see if we can factor. We notice that we have the typical descending order trinomial, so there is a chance that maybe the numerator will break into 2 binomials. So if I look at the 2x squared, I can think of maybe breaking it into 2x and x, and I'm going to try to make this just a little bit bigger. This box is pretty small, so what I'm going to do is this, if you don't mind. I'm going to say f of x equals, and then I'm going to write down the fraction below so I have a little bit more room to work with. So the 2x squared minus 5x minus 3, there. I'm going to break the 2x squared using 2x and x. And then if I play around with this 3 a little bit, I'm going to come to the realization that my 3 would go there and my 1 would go there. So that if I have an outer sign that's negative 6x and an inner value of positive 1x, I will have achieved this negative 5x. We'll do something similar for the denominator. And we would see that hopefully it breaks apart into x minus 3, x plus 2. Please note that it does not matter which order that you would write the pair of binomials. That would answer the first column. Second column says identify the restricted values of the function. For my students, this is something that we talked about a few units ago. And the restricted values are just simply the values of x that would create zeros in the denominator. You probably don't have to show work to find these, because if you set each of those individual pieces equal to 0, you're going to come up with the answers of x equaling 3 and x equaling negative 2. Now, a lot of people have asked me, what is the best way to present these? And to be honest, you really have a couple of options. If a student were to write the restricted values are x equal 3, x equal negative 2, I would understand that the state of equality using an equal sign coupled with the word restricted implies that these are values that you really don't want. But I also want to tell you that if you put does not equal, you would essentially be answering the same question. You're just now being a little bit more specific and saying these are the values that x cannot take on. All right? As a teacher, to be honest, I happen to like this notation because I think it emphasizes the whole idea about x not being able to take on those particular values. Now, in the third column, it says to rewrite the function in simplified form. So we'll take f of x equal, and then we look and see, do any cancellations take place? And I'm going to go ahead and go back to this first column, and I'll use a different color to cancel my common factors of x minus 3. And we see that what we've got left is a 2x plus 1 in the numerator, and of course an x plus 2 in the denominator. Well, that's all that third column is asking for. We move to the fourth column. Identify and classify the discontinuities from the graph of the function. Well, this does say that we're going to look at the graph. So I'm going to move back to the previous page, looking at the graph of f of x. And one of the things that we notice right away is that there is a discontinuity that occurs right here where this vertical asymptote appears when x is negative 2. So without question, x equaling negative 2 is a discontinuity. Now, it does want us to classify. Now, the classification can take on a lot of different words. Do you say removable? Do you say non-removable? Do you say point? Do you say jump? I would like to go ahead and use the following options. These discontinuities will either be a point. Jump would be an option normally, but you're going to find out that that's not going to be the case with any of these rational functions. We'll talk about that later. Or you could have a vertical asymptote. And because the vertical asymptote is a very long phrase to write, I will allow you to say VA. Typically in my class, if you're working a solution to a free response question and I see the letters VA, I will certainly understand what that means. As a reader for AP Calculus, if a student were to write VA on their tests booklets, I know that that refers to a vertical asymptote. So we've said that the vertical asymptote would occur when x is negative 2. It's a very powerful way to explain x equal negative 2. Having that x equal is going to be very important. We'll talk about that. Now, if I return back to the graph, I notice that there was another discontinuity occurring here where the hole was, and that's at where x is 3. And so for right now, I'm going to allow you to say that there's just simply a hole And we'll just use the same notation, put a colon, and the whole occurs when x is positive 3. Fourth column, or I'm sorry, the fifth column. What factor cancels out of the function and what type of discontinuity occurs at its restricted value? So if we go back to this first column and we see, well, what factor did cancel, we find out that the answer was the x minus 3. What type of discontinuity occurs there? Well, that's synonymous with this x equal 3, and so that's going to produce our whole. What factor does not cancel out of the denominator, and what type of discontinuity occurs at its restricted value? Well, that factor, of course, was x plus 2. And in this case, that's going to produce our vertical asymptote that we saw here in our fourth column. And that seems to be the goal of this particular lesson, to understand that whenever we have situations where denominator factor cancels, those are going to produce our wholes. On the other hand, if we have denominator factors that do not cancel, those are going to produce our vertical asymptotes. Now, we can't forget, both of them are still considered discontinuities. They're both restricted values, whether they canceled away or not. But determining what type of discontinuity is highly linked to whether or not they cancel. I'm going to pause the video, and I'm going to encourage my students to work through example B, and then resume the video when you're finished so that we can check your answer. Or let me rephrase that. I'm going to have you pause the video and then work through part B, and then resume the video to check your answers. All right, hopefully you had no trouble figuring out the solutions to part B. You can see that in the first column, I factored the numerator and the denominator. And then I see that the two denominator values, x plus 3 and x minus 1, would equal 0 at negative 3 and positive 1 respectively. So I'm going to choose to use the does not equal notation to highlight the fact that those are restricted values. Then, for the third column, rewriting this in simplified form is a matter of us looking at the fact that x plus 3 cancels away, and we're left with x plus 1 over x minus 1. So identify and classify the discontinuities. We have a vertical asymptote at x equal positive 1, and we would have a whole at x equal negative 3. What factor canceled out of the function, and what type of discontinuity occurs? Well, the x plus 3 canceling away leads us to finding the whole, and the factor that does not cancel, the x minus 1, leads us to finding the vertical asymptote. I'm going to go ahead and pause this video just for a moment so that I can fill in C and D, and then I'm going to go ahead and resume. And I would encourage you to do the same so that you can just check your answers, especially if you had any trouble with part B. But if you're understanding parts A and B, it's probably likely that you're getting the basics of this, and you're ready to move on to the next part. So here you can see the solutions for both C and D. One of the things to emphasize is when we get to the fourth column, the one in which we are identifying the discontinuities, despite the fact that the directions said to use the graph, so if we look at, say, P of x here in part D, we see that there should have been a vertical asymptote at x equal negative 3. And lo and behold, if I do look at the graph P of x, we indeed have that vertical asymptote here when x is negative 3. We also happen to see a whole when x is negative 2. It's likely at this point that you've discovered that you really don't have to look at the graph to be able to answer those questions, because you've discovered that if a denominator was to cancel away, like in the case of the x plus 2, that's going to lead to you finding a whole. But if the denominator does not cancel away, then that's going to allow you to find the vertical asymptote. Just be sure that you set these values equal to 0 to find the specific value. Anyway, that'll take care of this video, and hopefully this helps you out, and I'll see you next time.